Good morning. This is Dr. Shankaraiah, Assistant Professor in Department of Physics, IARE. So I am discussing about computer simulations of multifunctional materials. So in the last lecture, I have discussed about this. What is a computer simulations and what is and history of computer simulations. For example, how did it start and what are the way did they use to understand different systems. So today I am going to discuss about statistical mechanics. So in the last lecture, when I discussed about the history of these computer simulations, I have mentioned we apply different models that are available in statistical mechanics to study different properties of physical systems. So in this lecture, I will discuss about what is this statistical mechanics and what do we do in this branch of physics. So a macroscopic system consists of a very large number of microscopic constituents. For example, a gas in a container. A gas in a container contains large number of molecules. It is typically of the order of Avogadro number, that is 10 power 23. So this is a macroscopic system. So gas is a macroscopic system. So the microscopic constituents are the molecules of the gas. Gas is a macroscopic system and its microscopic constituents are the molecules of this gas. So the number of molecules N is typically of the order of Avogadro number, which is 10 power 23. And each molecule requires 3 position and 3 momentum coordinates for the complete specification in classical mechanics. So we know about classical mechanics, where we construct Lagrangian and Hamiltonian to study the properties of a system, and to use classical mechanics to understand or to study a gas. We need 3 position coordinates for each molecule and 3 momentum coordinates for each molecule. So basically, there are 6 coordinates are required for this complete specification of a single molecule. The entire macroscopic system at any given instant of time can thus be specified by a string of 6 numbers, which defines in a sense a microstate. So to define a microstate for this macroscopic system of a gas, and which consists of Avogadro number of atoms N, that is roughly 10 power 23. We need 3 position coordinate and 3 momentum coordinates. Totally, we need a string of 6 into 10 power 23 numbers to specify a single microstate. So in a phase space of 6 dimension, the system is represented by a point in classical mechanics. In classical mechanics, we can represent this system in a 6 dimensional phase space by a point, or more precisely by a phase space element of volume h power 3n. Because of quantum mechanics, we cannot specify position and momentum simultaneously. So it is clear that the number of microstates associated with the system is extremely large. So as I mentioned, at a time t, to specify a microstate, we need 6 into 10 power 23 numbers, a string of 6 into 10 power 23 numbers. As the time proceeds, the system is switching from one microstate to another microstate. So the number of microstates associated with this macroscopic system, which is gas, is extremely large. So in a classical picture, the point representing the system traces a trajectory in the 6 dimensional phase space with time. So we are representing this gas at any time t by a microstate. So the gas the molecules of the gas are moving, so the microstates are also changing with time. And we representing this gas in classical mechanics by a point in a 6 dimensional phase space. So as the time proceeds, this point in phase space traces a trajectory in time. So keeping track of this 6 into 10 power 23 numbers as a function of time is neither feasible nor practical. So at any time, to represent a microstate, we need 6 into 10 power 23 coordinates or numbers. position and to represent position and momentum coordinates. So as the time proceeds, we need at every time we need 6 into 10 power 23 numbers. So to understand this gas, the macroscopic system, we need to keep track of these 6 into 10 power 23 numbers in time, which is very difficult or not at all practical to save this data, right? So we need a statistical approach to understand this macroscopic system that consists of an extremely large number of microstates. So any experimentally measured equilibrium macroscopic property is a time averaged quantity. So if we are doing any experiment on a system and obtaining a macroscopic property, for example, a pressure or temperature of a gas, these are macroscopic properties. And how do we obtain these macroscopic properties in an experiment? We take the time average. So this time averaged is nothing but the averaged over the phase-space trajectory traced by the macroscopic system during the observation time. So how do we understand this? If you are using classical mechanics, in classical mechanics we represented this system by a point in a 6th dimension, and as the time proceeds, this point, the system traces a trajectory, and you are taking the average of this phase-space trajectory to obtain any macroscopic property to compare with the experiment. So let us assume that during the experimental observation, during the experimental time, the system visits all the microstates consistent with constraint on volume, number of particles, etc. So this is called ergodicity assumptions. So the gas has extremely large number of microstates. And during the experiment, we are carrying out experiment on this macroscopic system gas. And in our experiment, during our experimental time, the gas system visits all the microstates that are possible in the system, and system visits all these microstates during this experimental observation time. So this assumption is called ergodicity assumption. So this ergodicity assumption is fine since the observation time scale is very large compared to the time scale over which the system switches from one microstate to the other. In a real system, the switching from one microstate to other microstate is very, very small compared to the experimental observation time. So it is fine that the ergodicity assumption is fine because the experimental observation time is large compared to the time scale of the real system for switching from one microstate to the other microstate. So we can then equate this experimental time average to an average over a suitable static Gibbs ensemble of microstate. So what I am saying is that during the experimental observation or during the experiment, the system visits all the possible microstates. Okay, so now I can compare this experimental average to an average over a ensemble of microstates. So what I am going to do is that I am going to collect all the microstates, whatever are available for this physical system. I am going to collect all these microstates, and I am going to call this as ensemble of microstate. So for this macroscopic system of gas, I am going to collect all these microstates possible for this gas system, and I am going to take average suitably over this ensemble of microstates and compare this ensemble average to a experimental time average. For such a scheme to be successful, we must recognize that a macroscopic property is basically statistical in nature. If you are going to compare the ensemble average to an experimental average, the property which you are going to obtain should be statistical in nature, so that you can use this ensemble average to compare with experimental average. So are there any quantities or properties of a system that are statistical in nature? Yes. For example, pressure is the average momentum transferred by the molecules colliding with the walls of the container. Pressure is the average momentum transferred by the molecules that are colliding with the walls of the container. And entropy is the logarithm of the number of microstates accessible to the system. Temperature is average kinetic energy, and specific heat is a manifestation of the fluctuations in energy. So there are properties of a system that are statistical in nature. So you can use ensemble average suitably, and you can obtain properties, and you can compare with experimental time averaged quantities. So when the system is in equilibrium, the macroscopic properties of a system do not change with time. So that is the reason why we can collect all the microstates, because the macroscopic properties are not changing, but the microstates are changing with time. So you can collect all the microstates of the system in an ensemble and obtain a property by taking ensemble average and compare to an experiment. Hence, a macroscopic property can be defined as a time averaged quantity over an underlying stationary stochastic process, or equivalently an average over a suitably defined Gibson cell. So we can obtain a macroscopic property by taking time average in an experiment, or we can obtain a macroscopic property by taking ensemble average in a simulation. So then we can compare these two quantities. So the associated fluctuations in these computer simulations where we collect these ensemble of microstates, the fluctuations are inversely proportional to the square root of the system size, and hence are negligibly small. If you are going to take larger and larger number of particles in a system, then the fluctuations associated with any physical quantity is going to be smaller and smaller. So this is directly a consequence of the central limit theorem, which we have discussed, which we will be discussed in the future lecture. So what is the central limit theorem? What does it tell? So the central limit theorem says that the distribution of the n independent and finite variance random variables converges to a Gaussian distribution in the limit of n tending to infinity, and it has a variance that is proportional to n. So the central limit theorem says if you increase more and more number of random variables, then the variance will be proportional to n as you take n larger and larger, and as it tends to infinite. And the standard deviation of this arithmetic mean of these n random variables is inversely proportional to the square root n. As n becomes large and large, the standard deviation becomes smaller and smaller. What do you mean by n is becoming large and large? That means we are going to take a system with larger and larger number of particles, so that we are mimicking a real system where it has Avogadro number, which is 10 power 23 number of atoms or molecules. Physically, this implies that the fluctuations of a macroscopic property from its average is extremely small and inversely proportional to the size of the system. So the fluctuations will be smaller and smaller as we increase the size of the system. So clearly it is the largeness of the number of microscopic constituents, that is number of atoms or number of molecules of macroscopic system gas, that gives rise to the robustness to the macroscopic behavior of a system. So if you want to get closer and closer, whatever quantity you obtain in a simulation by finding out the ensemble, the quantities that you obtain in simulation will be closer and closely comparable to the experimental value as you increase your system size. So the question is, what is an ensemble? I've been saying that we need to connect an ensemble of microstate and take an average of these ensembles to compare with an experiment. So what is an ensemble and what is a Gibbs ensemble? So to understand what is the ensemble, consider an experiment which has more than one outcome. Okay, so we are to understand what is an ensemble, we need to consider experiment that has more than one outcome. And now we collect all the possible outcomes of the experiment in a set called sample space. Okay, so we are considering an experiment, and the output of this experiment is not one. There are many outcomes. There can be more than one outcomes, and we are collecting all the outcomes of these experiments in a set, and we are calling this set as a sample space. And let the probability of occurrence of any outcome is not zero, and it is greater than zero. And when we sum over all the probabilities of these outcomes, it should be 1. So the sample space and the probability define the experiment. So physicists, however, use a single notion of an ensemble introduced by Maxwell, and it is denoted by omega e. The members of this ensemble are drawn from the sample space omega. So we construct an ensemble which we call it as which is introduced by Maxwell. And how do we construct this ensemble? By drawing the outcomes from the sample space omega. So, however, an outcome omega I appears in the ensemble n omega of times, so that we obtain the probability for that outcome omega I. So, to get the probability of outcome, the outcome appears as many times as to obtain the probability of that outcome. So omega cap E is the size of the ensemble. So we need to take this omega of cap E adequately large, so that all the outcomes of the experiment appear in the ensemble in correct proportion. That means all the outcomes occur as many times as to reflect its probability. So we do not specify any rule for the construction of an ensemble. We can employ Monte Carlo simulation, or we can use molecular dynamic simulation, or any other technique to construct an ensemble. So that is about an ensemble. So for example, to understand ensemble, you can take a simple example of tossing a coin. So take tossing a coin experiment. So there can be two outcomes, heads and tails. So the sample space contains two outcomes, heads and tails, right? And you can obtain the probability of occurrence of heads and the probability of occurrence of tails. Okay, so and collect these outcomes in a sample space, and then you can construct an ensemble for this experiment that contains these micro states as many times as to reflect the probability of these outcomes of heads and tails. So what is a Gibbs ensemble? A Gibbs ensemble contains microstates of an equilibrium macroscopic system under the macroscopic constraints operating on the system. So Gibbs ensemble contains basically microstates of a equilibrium system. Depending on the nature of the constraints, you can construct different ensembles. Okay. So first, for example, I am discussing about isolated system. So for which we can construct microcanonical ensemble. We have a physical system which is isolated system, and for this isolated system we can construct a microcanonical ensemble. Let us consider isolated macroscopic equilibrium system. Okay, we are using all the time, we are using equilibrium system, and the constraints on this isolated system are energy, volume and number of particles, EVN. These are the constraints. Collect all the possible microstates of the system into a set called omega IS. Isolated system IS, and omega is the sample space. Okay. So we are going to collect all the possible microstates into this sample space omega IS. All microstates of isolated system are equally probable. Okay, because all the microstates have equal same energy, all the microstates are equally probable. Also, because of the constraints, all the microstates have same energy, same volume and same number of particles. That is the reason why all the microstates are equally probable. So for this isolated system, we are going to calculate some macroscopic property, and we are denoting it by O of C, which is a macroscopic property of the system when it is in some microstate C. So we are going to obtain the average of this macroscopic property given by the equation. So average O is given by 1 over omega is sum over C belongs to omega is of O of C. O is nothing but the macroscopic property that is summed over all the possible microstates of this isolated system and divided by the total size of this isolated system. And in fact, the entropy of the system is given by Kb log omega s, where Kb is the Boltzmann constant and omega s is the total number of microstates of this isolated system. Thus, the probability P of C for an isolated system to be in a microstate C is 1 by omega s, because all the microstates are equally probable and omega s is the total number of microstates. So, the probability occurrence for any microstate is 1 over omega kappa s, which is the total number of microstates of this isolated system. And you can the probability you can construct, it can be written in terms of exponential of S by Kb, where S is the entropy of this system and is same for all the microstates. So for this isolated system, we can equivalently construct a microcanonical ensemble of microstates. A microstate C belongs to this isolated system occurs in this microcanonical ensemble as many times as to reflect its probability P of C. So we have discussed about isolated system. We have obtained the probability of occurrence of any microstate C. Right? So now we are going to construct a microcanonical ensemble for this isolated system, and in this ensemble, a microstate C is going to appear as many times as to reflect its probability of this isolated system. In other words, the number of times the microstate occurs in a microcanonical ensemble divided by the size of the ensemble equal to the P of C, the probability of occurrence of microstate, which we have obtained in isolated system. So we are going to construct this microcanonical ensemble of this corresponding to isolated system, and in this microcanonical ensemble, the microstate, any microstate C is going to appear as many times as to reflect its probability P of C. For an isolated system, all the microstates belonging to this isolated system occur in equal proportion, because all the microstates are equally probable and all the microstates have equal energy. So that is construction of a microcanonical ensemble for an isolated system. Okay. So there, the another system is a closed system. Isolated system does not exchange energy or number of particles with any other system. It is isolated, right? So there can be a closed system for which we are going to construct a canonical ensemble. Consider now an equilibrium macroscopic system in thermal contact with a heat bath at temperature say T. So isolated system is not in contact with any other heat bath. It is not neither changing energy nor changing number of particles. It was isolated system. For such an isolated system, total energy, total volume and total number of particles were constant, and we have constructed a microcanonical ensemble to obtain a macroscopic property. Now we are saying that now I am not going to take, I am interested in a closed system where the equilibrium system is in contact with a heat bath at a temperature T. So there is going to be exchange of energy. So volume is constant and number of particles are also fixed, but total energy is not fixed. Instead, the temperature of the system is equal to the temperature of the bath when the system is in equilibrium. So in this, for this closed system, temperature, volume and number of particles are constant. So this is a closed system where system exchanges energy with the heat bath but not particles. So for this closed system, we can construct a canonical ensemble. Let omega Cs denote the set of all possible microstates of the closed system at temperature T. And omega Cs is called the sample space of the closed system. Since the system exchange energy with the heat bath, different microstates belonging to this closed system can have different energies, and also the probability with which microstate occurs in a closed system is different, and it is found to be exponential of minus beta E, where beta is the inverse temperature 1 over Kb T, where Kb is the Boltzmann constant and T is the temperature. So in isolated system, all the microstates were equally probable because all the microstates have constant energy or same energy. But in closed system, the system is in contact with a heat bath, so there is exchange of energy, and all the microstates are not having the same energy. So the probability occurrence of a microstate, particular microstate, is not constant. It is found to be exponential minus beta E. So the probability of occurrence of a microstate C in a closed system depends on the energy of the microstate and the temperature of the system, because we found that P of C is directly proportional to exponential minus beta E. So the probability is depends on the probability occurrence of a particular microstate in this closed system depends on energy and beta, which is inverse temperature. Thus, to each microstate that belongs to this closed system, we attach a Boltzmann weight, which is e power minus beta Ec. The sum of the Boltzmann weights taken over all the microstates belonging to this closed system is called as canonical partition function. So we are defining a partition function for this closed system by Z of beta Vn, where beta is the inverse temperature, that is equal to sum over C belongs to omega Cs e power minus beta E of C. This is the partition function for the closed system. So now we are going to calculate a macroscopic property O of this closed system when the system is in a microstate C. So the average is given by this 1 over Z, which is a partition function, and sum over all the microstates over O into e power minus beta E, which is a Boltzmann weight. So to calculate this average macroscopic property, we can take an alternate approach. Okay, so let omega Ce denote a canonical ensemble of microstates belonging to the closed system. So now we are going to calculate this macroscopic property using or constructing a ensemble corresponding to this closed system. A microstate C belongs to this closed system occurs in the ensemble, canonical ensemble Ce, as often as to reflect its probability. So probability occurrence of any microstate P of C is given by this, where C is the microstates. So C belongs to the closed system occurs in the ensemble divided by the size of the ensemble gives us the probability. So the advantage of constructing a canonical ensemble is that a macroscopic property can be calculated as a simple arithmetic mean. What is the advantage of constructing an ensemble for a closed system is that we can just take the arithmetic average of this macroscopic property to calculate this average. Okay, so the arithmetic mean is 1 over omega of C cap, which is the size of the ensemble, and sum over all the macroscopic property values. That will give you the average of this macroscopic property. And the size of the canonical ensemble is taken to be large, so that even all the microstates with low probability also present in the ensemble in the right proportion. So when we construct a canonical ensemble for this closed system, we need to take the size of the ensemble very large, so that all the microstates occur as many times as to reflect its probability, so as whatever physical average macroscopic quantity we obtain using this ensemble average will be comparable to the experimental quantity. So that is the closed system. The third system is open system, for which we are going to construct a grand canonical ensemble. So we can proceed further and consider an open system in which there is an exchange of energy as well as particles with the surrounding bath. So closed system is a system where there is exchange of only energy, but open system there is exchange of energy as well as particles with the bath. So the constraints are now temperature, volume and chemical potential. So the open system can be found in a microstate C with a probability proportional to this Gibbs factor given by exponential of minus beta E plus mu beta n, where mu is the chemical potential and n of C is the number of particles in the open system when it is in its microstate C. So here the probability of occurrence of a microstate is proportional to this Gibbs factor, where you have beta E term and you have mu beta n term, where n is nothing but the number of particles. So the sum of the Gibbs weight taken over all the possible microstates of this open system is called grand canonical partition function given by this. This is the grand canonical partition function that can be constructed for a open system. So the average of a macroscopic property is formally given by this equation. This is the partition function, and sum over all the macroscopic property multiplied with the Gibbs factor, as we are constructing a grand canonical ensemble for this open system. So we can calculate the average by constructing grand canonical ensemble omega of grand canonical ensemble of microstate. So we can calculate this macroscopic property by taking the ensemble average by constructing a grand canonical ensemble. So the number of times a microstate C belonging to this open system occurs in grand canonical ensemble divided by the size of this grand canonical ensemble is given by the probability of occurrence of a microstate, and which is given by this exponential of minus beta E plus mu beta n of Q, where Q is the partition function. So the average is given by a simple arithmetic average when we construct this grand canonical ensemble for this open system. So which is given by this. So 1 by omega of G grand canonical ensemble, which is the total number of microstates of this ensemble, and multiplied by this sum over all the microstates of this average quantity, macroscopic quantity. So besides the microcanonical, canonical and grand canonical ensemble, we can construct other physical ensembles like isobaric, isothermal ensembles depending on the problem under consideration. So the choice of the ensemble is purely a matter of convenience dictated by the nature of the physical system under investigation and the nature of the macroscopic properties which we want to calculate. So the calculation of this macroscopic property as an average over a canonical ensemble of microstate can be generated by Monte Carlo simulation or molecular dynamics simulation. So I am saying that how the macroscopic properties can be calculated using different simulation techniques. For example, Monte Carlo simulations or molecular dynamic simulations. Once we construct these ensemble, we can calculate whatever macroscopic property we want. So in this lecture, I have discussed a construction of different ensemble. For example, microcanonical ensemble, canonical ensemble, and grand canonical ensemble, and how we can calculate the macroscopic properties using by constructing an ensemble, and that can be used to compare with experiment. So we can, and how do we construct this ensemble? We can use Monte Carlo or molecular dynamic simulations, and once we construct an ensemble, we calculate the average quantities as a simple arithmetic average, and then we can compare with experiment. Only thing is that the size of the ensemble should be as large as big, so that we can, the fluctuations associated with this average quantity in ensemble average should be smaller, so that it is comparable with the experiment. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.